we're now going to talk about ways to compute limits of sequences. We want to be able to take advantage of some of the things we learned in earlier calculus classes. We learned in Calc 2, or actually maybe even Calc 1, I forget exactly which one, that we can find the limit of a function like this, say 2x squared minus 3x plus 1 over x squared plus 7, and that limit is 2. How did we compute that? Well, we saw that 2x squared minus 3x plus 1 over x squared plus 7 is actually, if I divide numerator and denominator by x squared, I get 2 minus 3 over x plus 1 over x squared over 1 plus 7 over x squared. And we had limit laws when we take limits of functions. The limit of 2 minus 3 over x plus 1 over x squared over 1 plus 7 over x squared is just the limit of the numerator over the limit of the denominator. And to find the limit of the numerator, we just take the limit of 2, which is 2, plus the limit of minus 3 over x squared, which is 0, plus the limit of 1 over x squared, which is 0, all as x goes to infinity. And for the denominator, the limit is just 1 plus the limit of 7 over x squared, which again is 0. So you get limit of the numerator is 2 over the limit of the denominator, which is 1, and you get the limit to be 2. This is just using the limit laws for functions. We can apply this to sequences. So I claim the limit is n goes to infinity of 2n squared minus 3n plus 1 over n squared plus 7 is 2. Now, how is this different from this? Normally in mathematics, you could just call your variable anything you want, and these two you might think mean exactly the same thing. But it's a convention that when we use a number like m or n, we're talking about discrete quantities, meaning n equals 1, 2, 3, etc. So this limit here means the limit of the sequence. In other words, it means the same thing as saying the sequence 2n squared minus 3n plus 1 over n squared plus 7 approaches 2. Whereas when we talk about a variable like x or y or z, we're normally talking about a real quantity and just saying as the real number x gets big, what can we say about the values of this function of x? Now, if this limit statement up here is true, limit as x approaches infinity of this function of x is 2, that means whenever x is big, the value of this function is close to 2. Well, if we restrict our attention to integers, of course they'll be close to 2 as well when n is a large integer. So knowing that this function has a limit 2 tells us immediately that this sequence has a limit 2. We put this more precisely, here's what we just said before, we put this more precisely in the form of a theorem. The theorem says the following thing. If for some function f we know the limit as x approaches infinity of f of x is the real number L, then the sequence f of n has that same limit. In other words, this sequence f of 1, f of 2, f of 3, f of 4, etc. converges to that same number L. This is the theorem I was just talking about. Let's look at an example of this. Let's say you look at the sequence arctangent of 1, arctangent of 2, arctangent of 3, arctangent of 4, etc. Well, we all learned in Calc 2 that the limit as x approaches infinity of the arctangent of x is pi over 2. So that tells us that this sequence also has limit pi over 2. Here's another theorem. If you have a sequence which you know converges, it converges to some number L, and you have a continuous function, here's a very, very important that f is a continuous function, or at least continuous at that one number L. If it's continuous everywhere, great, that will certainly be satisfied. Then if you look at a new sequence, f of a sub n, then that will approach f of L. In other words, the limit of f of a sub n is just f of L. Here's an example. We already showed that the limit as n approaches infinity of n minus 1 over n is equal to 1. This was the same as saying that this sequence 0, 1 half, 2/3, 3/4, etc. this sequence converges to 1. That's one of the ones we talked about in the last lecture. We know that the arctangent function is continuous everywhere. The arctangent function, you'll remember, has domain which consists of all real numbers, and it's a continuous function. So what does that tell us? It tells us, if I look at this sequence, arctangent of n minus 1 over n. In other words, this sequence, arctangent of 0, arctangent of 1/2, arctangent, we don't need that in the notation, arctangent of 2/3, etc. This will have a limit which is just arctangent of the limit as n goes to infinity of n minus 1 over n, which is arctangent of 1, which, as you all remember, is pi over 4.